Okay, so let's continue with this regularization. So last lecture we defined this regularization just for like determinant of Laplacian, but the method is very general, so it can be applied to regularizing infinite products in general. So infinite products. So the idea is that we have this sequence, like number one positive, so strictly positive. And this sequence is going to infinity. And our goal is to understand or to define this how to regularize this infinite product. So there are, as I said, different methods for regularization. So one method that we started last lecture is Zeta Regularization. You see, this has nothing to do now with Laplacian or manifolds or anything. This is just a question like this. So what you do, obviously, you form a kind of zeta function attached to this. So lambda of S, you just say this is sum 1 over lambda I to the power S. Well, lambda is this sequence. I call this sequence, all of them, just collectively lambda. So then what we want is that some conditions should be satisfied. So then these are some extra assumptions we have to assume. First of all, that this guy is convergent. In some right half plane for a real part of S, say some right half plane. And second, let's assume that it has meromorphic extension to C. Extension to C. And the third part is that let's assume that this function that you extend meromorphically is actually holomorphic at 0. This is that lambda S is holomorphic. At S. So if these three assumptions are satisfied, you can go on and define this infinite product as exponential of minus zeta prime lambda at 0. Okay, so this you can do like what we did with eigenvalues of Laplacian, and then we defined regularized determinants last lecture, but this we can do in general. So this has some nice properties. For example, some obvious properties is that, for example, so if you have such a sequence, if you just cut out the first n of them and multiply them together and then multiply by this infinite product lambda I. Now I given equal to n plus 1. So this is the obviously ordinary product. This is regularized product, and this is equal to product of all of them. This is very easy to see. So in kind of products, this is natural to expect, and in this case, it's true. Second condition, not condition, second property of this product is that if you scale these quantities by some like positive number C, for example, I mean, if you do product of C lambda I over I by this method, this is like taking, I think this is like exponential of minus zeta A, not minus actually, zeta lambda at 0, yeah, times lambda 1, lambda 2, lambda. This is also easy to see. But so the value of zeta at 0 appears here. The value of the derivative of zeta at 0 is here. And but anyhow, so that's easy. So it's like c to the power infinity is equal to exponential of zeta at 0. Okay, so this you can do, but I mean, but then some obvious things that you want to be true, they are not true. I mean, so there is this warning. I mean, for example, you might have a sequence of product of two things, and you might hope that, yeah, the infinite product of termwise products is separate. That's not true. In general, product of lambda I mu I over I is different from product of lambda I times product of mu I. So in other words, this sort of product is not multiplicative in a way. So this lack of multiplicativity is interesting. So you need an example for this. So I would give it as an exercise. Exercise is find an example. So exercise, yeah. Yeah. So now, the question is, for what sequences we can do this? What sequences have this property that we are guaranteed 1, 2, 3 holes, and then we can do. The answer is we don't know. This is a very hard problem. We don't know the answer, but there are sufficient conditions that if those conditions are satisfied, then this technique works. And those sufficient conditions are exactly like the asymptotic expansion of the heat current that we did. So let me then write it here.
Sorry, can I just ask a quick question?
Oh, sure.
In that second property of this product, you're saying that it's independent of the value of C because you have, what is that, zeta of lambda 0? It's the same factor no matter what, or is that supposed to be zeta lambda C?
Oh, I'm sorry, this is C, yeah.
Oh, that's a C, okay. Okay, sorry.
No, I mean, thank you for picking this up, because I just, I don't have my glasses, I just copied from my notes. I just confused C by E. So
We
that's.
restrict to C non-zero.
What's that?
Is it necessary to restrict to C non-zero?
Oh, yes, absolutely. Of course. I mean, if C is zero, then C is zero, this product is not defined for infinite products of zeros because they don't go to infinity. And this zeta function is just really is doomed. I mean, yeah, you cannot even define it because lambda i's are all zero, then 1/0, it doesn't work. So, yeah, absolutely.
So it's even positive, right? This is for positive C.
Yes. Oh, yes. These numbers are positive. Yeah. Oh, yeah. I believe there are ways to extend this to sequences of complex numbers that still go to infinity, but they should remain in some sort of sector or something. I mean, there is a way to extend this to infinite products of complex numbers also, at least with some conditions. Yeah, I think it's possible. But you should be able to kind of, yeah, because you need to fix a branch of log, and then your numbers should be in that branch, I think. Yeah, something like that has to be true. Now that's a good comment. Yeah. Okay. Any other questions or comments? Okay. So anyhow, I'll keep it as well. So so let us define this theta series. Again, very general for just this some exponential of minus lambda I t. So this is a theta series. Like theta function was similar to this. And let's assume that this theta series satisfies these three conditions. So first of all, theta lambda t is convergent. So okay, I have to write something, right? Assume this is convergent for any t positive. Yeah, so this series, let's assume, is convergent for any t positive. Second, let's assume that there exists an asymptotic expansion, theta lambda t. I mean, okay, asymptotically is given by some. Now, an tn. So n from my notation is going to be a bit different. Yes, n from minus d to infinity. Okay, so this condition means that there exists an asymptotic expansion like this as t goes to 0. And of course, the meaning of this asymptotic expansion is that we can always write theta t as equal to, if you cut down somewhere at finite step n minus d to some k, an tn, right? And then it's O, capital O of t to the power k plus 1. It's a meaning of asymptotic expansion. So the error that you get is of the order of t to the power k plus 1 if you cut your series at maximum order k. So this is for t, of course, small. I mean, so there exists, the statement is that for any k, there exists an epsilon depending on k such that this holds near 0. We're not saying this holds all the way away from 0, but near 0, near enough, depending on k, then this is going to be like that. So example of this, of course, was these eigenvalues that we got from Laplacian, right? Laplace eigenvalues. On closed manifolds. Actually, but there is even more. So now I'm going to say on closed, on compact with boundary even. So, or compact with boundary. with the smooth boundary. I mean, everything here is smooth, but there is boundary, smooth boundary. The Laplace, I mean, okay, so either Dirichlet boundary condition or Neumann or some several classes of boundary conditions are okay for this. You can prove that expansions like this hold, except that now this n is not moving through integers. N can move through integers plus half, for example. They move by half. That's okay. And this d, I'm not assuming is integer. D could be half integer, or it could be even more general. I mean, this is very general scheme. So this is more general than symptotic expansion of eigenvalues, but still quite strong. Okay, then using exactly same technique as we did for Laplace, you know, I mean, like what we did was then using, so this was an Elaine transform. So you can show that this zeta lambda s is equal to 1 over gamma s, integral 0 to infinity. This theta series, lambda t, t to the s, t, dt. So this is true for real part of s very large, that guarantees this is defined. Notice I did not subtract anything here. So from the heat trace, I had to subtract the dimension of zero modes. But here I'm not, because I'm assuming that these eigenvalues actually are all positive. I threw away zero eigenvalue from beginning. I mean, these are not eigenvalues anyhow. These numbers are all strictly positive. So I do get this function already itself at infinity is rapid decay, this series. So this integral is already easily convergent at infinity, and at zero is okay for, yeah, that range. And that's everything about this integral is fine. Okay, and then using, so this was just Melina, but then using 2, then you can show that that actually this zeta has the 3 properties that we want. So this is, so that's satisfies. In other words, so this is an example of a good sequence of numbers that we can define infinite products of. Defined. Okay, so it's defined as exponential of minus zeta prime lambda at 0. So this is defined. Okay. Now, in terms of computing these things, there are some nice results. So you can, there is a book actually, I should say, there's a book by Souley. It's called, what's it called? Introduction to Arakelov geometry, I believe. It's a book of algebraic geometry and number theory, but it has very nice section on these heat kernel techniques, and also these things, you can find it there. So this result I'm going to give you, you can find it in the book. It's now very easy to prove using what we know. So the lemma or proposition is the following is that zeta lambda 0 is equal to A0. Remember, we had this asymptotic expansion for the theta series. A0 comes from that. Okay. And second of all, this is equal to finite part of the integral. So this is a term I will define finite part of the integral. Yeah, okay. Epsilon to infinity theta lambda t dt over t plus gamma A0. So gamma is Euler's constant, as we had before. Gamma is Euler constant. This was the name of, I believe, sum 1 over k from 1 to n minus log n. It goes to infinity. It's a positive number, as we saw. It's near 0.5, 57% or so. Okay, so now the only thing I have to define is what is this finite part. So this finite part is also a regularization. It's due to Hadamard. So let me just quickly say finite part. So what does finite part means? Sometimes you have a divergent integral or divergent series or something, and then you notice that if you stay away from this, like the point, the limit point of your domain, then you notice that the integral can be expanded in terms of some polynomials and some log functions and products of these two things. And these are the ones that give you divergence. So you throw away those parts and keep the first term that's okay. And that's the finite part. So just instead of giving a formal definition, let me give you an example. E.g., assume in an integral like this, for example, integral epsilon to 1 f of x dx, you can write it, imagine, as a function like this, as I'm not sure, 1 over epsilon to the k, well, something like a plus b. So let me put it like epsilon squared, epsilon cubed, plus c log epsilon, plus some products of these divergent terms. And then there is this first term, A0, which is non-zero. I mean, so this is near zero. So obviously, if you want to take integral from 0 to 1, like f of x dx, this sort of calculation shows that this is divergent. Your integral is divergent. But you define the finite part of this, finite part of this to be A0. Just take this. So this, I think, is due to Hadamard, but it must be very, very old idea. I mean, people, Cauchy, I'm pretty sure Cauchy has used this, these things, and Euler, and people just must have noticed this. So it's interesting that it appears here also. this integral is divergent. But if you take its finite part and you correct it by this amount, it gives you the value of zeta at 0. And this is what we want because that gives you the infinite product. So here it is. I mean, this divergent integral, if you regularize it, of course, I mean, here is not 1, it's infinite. But this integral, there is no problem with this integral as at infinity. You can just subtract, you just epsilon to 1 and then 1 to infinity. 1 to infinity is just fine because this is rapid decay at infinity, right? So that's, I mean, the proof of this is then it's not difficult using just asymptotic expansion as I did. So, okay, so just simple example of this. 0 to 1 dt over t. I mean, this is just, so what is that? Well, I mean, we are interested in finite part, right? Well, I mean, that's very easy in this case. Just write epsilon to 1 dtt is just what? Minus log epsilon, right? And you discard that, so there's 0. So this is 0. Now, you may complain, say that, hey, you just wrote it like that, but then what if someone else, because you didn't tell what the other parts are. Yeah, we don't know what the other part. And someone may have a different series of such numbers. Yeah, different series of such numbers, and then you have ambiguity in the definition of finite part. But that's not the case because you notice that if two such expressions should be true, then these guys have to have same behavior near 0. Then immediately implies that A, B, C, A0 have to be the same. So it's like a uniqueness of asymptotic expansion if they exist. That's okay. So that part is okay. And then you can just go on and define this in terms of, okay, so the proof of this, as I said, is not difficult. You just use this asymptotic expansion and then you integrate term by term and just, okay, so that's similar to what we did for Laplace eigenvalues. Okay, so there is a lot to be said about these techniques of regularizations, right? We didn't even scratch the surface. There is this Pauli-Villar's regularization. There are dimensional regularizations. There are many different schemes, very important, very deep, and there are relations between them. So we are not. For us, zeta function is the primary tool for regularization. Okay, so that's that. I'm going to switch gears now and move to another application of this, actually application to geometry and topology of this Zeta regularized determinants, which I will start now. Do you have questions or? Yeah, this book is by Souley, I think. Oracle of Geometry. Introduction to Oracle of Geometry. Souley et al. I mean, there is a group of authors. Okay. Oracle of Geometry. Yeah, it's, if you want to know the subject, it's also extremely well written. It's a great book, actually. Yeah. So, let us now move to something very classical, which is actually due to Ray Singer. So this is Ray Singer Analytic Torsion. So this is same paper I mentioned in last lecture, where actually Zeta regularization was introduced. They introduced it in order to do this. So this was, they have together, I believe, 2 papers, and then this is in the first paper. The second paper is a holomorphic version of this. So what is this? So now imagine you have a Riemannian manifold as before. So this is closed, maybe connected. Manifold. So assume that you have a representation of the fundamental group. Fix a representation rho of fundamental group of n to GLV. So this V is a finite dimensional, say, complex vector space, right? So this is a finite dimensional representation. Then what you can do, you can get a vector bundle over M. Let's call this E. So this is this associated vector bundle to rho. So how this associated bundle to rho is defined? We can just take, say, E to be, so imagine you have this universal cover of M. Then what you can do, you can just take M tilde, semi-direct product, cross product, whatever, with V with respect to action of, I mean, pi1 really, or rho, if you want. I should say rho. You see, rho, this group acts on this space in the obvious way, and on this one in by rho. So I don't know how to put this. This is so yeah. I mean, by definition, this is really like M tilde cross V divided by an equivalence relation. The equivalence relation is that we are declaring that M G and V is equal to, so yeah, equal to M and rho G V, right? For all G belonging to pi1 M. So you do get a vector bundle like that. So this bundle, because it's coming from a representation, is a flat bundle. So this bundle is flat. So in other words, there exists a connection on this bundle. The connection I denote by nabla. It is a flat connection. On M, on E, I should say. Okay. Now, in general, when you have bundles, you can extend this whole differential form business to differential forms with coefficients in this bundle. So we can define this de Rham complex with coefficients in E. This n is dimension of the manifold. I mean, then there is extension of this exterior derivative using this connection to these guys. So this is sometimes denoted by d nabla, but I may just drop nabla. So this is called the de Rham complex. Of M with coefficients in E now. So, right, so that's what we do. Then what you can do, you can equip this vector bundle with a Hermitian inner product. So equip Hermitian, fiber-wise inner product. This we can do. Then you can do the adjoints of this. Everything. By the way, I mean this this guy, like omega p of M and E. Oh, I mean, of course, this is just you can say this is omega p of M. Tensor smooth sections of E. But this tensor should be over C infinity of M. So this is the space of smooth forms on M, P forms on M with coefficients in E. So if you write in some local coordinate, like usual expression for forms, those coefficients now are sections of the bundle. They are not usual functions. So that's what it is. And then using this connection and the D, you can extend exterior derivative to this, and Hodge star, everything works in this context, and it goes on. So then we can define the Laplacian. So maybe P. Now everything, of course, depends on this rho and on the metric, on the base manifold and all this, but just let me define it like this, Laplacian, sorry, to be D, well, I mean the nabla, D nabla star plus D nabla star, D nabla, so this goes from omega P of an E to itself. It's like a usual Laplacian that we had on functions and forms. Now we extend this Laplacian to forms, P forms with coefficients on in E. Okay, so this business works. Then what do you want to do? Then, of course, this operator has a discrete spectrum again, like usual Laplacian. So let me write it. So each delta P has discrete spectrum. Okay, I mean, I don't designate P anymore. I just say lambda 0, maybe less than equal to lambda 1, like that. So in particular, for each P, we have this spectral zeta function. Now I have to write something. Okay, so it's going to be a heavy notation. So I just put P, but I know that this is with coefficients in E, so using this spectrum, so you have to throw away zero spectrum. There may be zero in the spectrum. Okay, so again, this we can show that this zeta function of this Laplacian for this flat bundle is nice as meromorphic extension. It's yeah, and it's regular at 0. Then we can define this determinant. So log that prime of delta P by definition equal to minus Z prime P at 0 is defined. Okay, so this is all defined and nice. Now, what is this analytic torsion? So, definition. So, this is racing here. The analytic torsion of this gadget that we defined, I believe the notation is T of M, and this representation rho is by definition is equal to 1/2 sum -1 to P plus 1, I'm not sure, P plus 1 P log that prime of delta P. Okay, so okay, so now this definition is so first of all, let me make sure that I've got it right. No, actually, I think this P is okay. Otherwise, I'm completely okay. Log.
Isn't this log of T?
Log of the torsion. Yes. This is log. Yeah. Is that what you wanted to say? Log of this guy. Yeah. 1/2 this one. Yes. That's okay. Of course, you can write TMP by exponentiating, and then if you exponentiate, you get TM torsion. I mean rho. Sorry. Rho and P. So that's equal to, so I mean, it's square is really equal to products of determinants of Laplacians, like this, determinant of delta P. Here is -1 to the power P, P. Although still this P and P plus 1 bothers me. P plus 1. Huh?
I think it's correct.
You think it's correct?
You also can.
What's that?
Zeta prime of at 0 instead of. I mean, it's the same. But
Which one?
like that of the Laplacian is the same as the prime at 0.
Oh yes.
I mean, for simplicity.
Oh yeah. This is the prime. Yes, of course. Yes. It's here. Is that what you?
Yeah.
Oh, that's why then -1 creates a P plus 1. Is that what you're saying?
Yeah.
Okay, but anyhow, so this is the one. Now, so of course, I mean, this definition is completely mysterious and obscure. I mean, what is this? I mean, why this quantity? Where it came from? I mean, so you have to spend quite a good deal of time and invest time to okay, so you have to read Racing here and then literature. There's a lot of work after that. See what it means. Notice that it's some kind of alternating products of determinants. You see, in Euler characteristic, we had alternating sums of dimensions of cohomology. Here is alternating products. So so the even ones is on the top, odd ones in the denominator, but there is this P factor, which is different. I mean, it's not totally you cannot say this is multiplicative analog of Euler characteristic because there is still this P factor here, which it's not clear right now why there should be this factor P. I mean, the whole thing is a big mystery. So, okay, so, but these methods of spectral geometry gave us this, gave Raysinger this opportunity to define this concept. I mean, the one point is that this is related to another invariant of manifold, which is a cohomological invariant. So this Raysinger conjecture they conjectured, but then later proved by Chigger-Muller there are two independent proofs separately. I believe their methods also is different. They prove that this analytic torsion is closely related to Reitmeister torsion. So analytic torsion is related. I mean, I don't want to say it's equal. There is one more factor which is missing, but that's it. Is related to Reitmeister torsion. But there is a condition. This Reitmeister torsion was defined under the condition that this Durand complex with coefficients in E is acyclic, assuming that actually cohomology of N, Durand cohomology of N with coefficients in E is actually 0 in all dimensions. So you need to assume that your representation is such that gives you a trivial cohomology. Okay, so gives you a trivial cohomology, and then there is this recipe of Reitmeister, which is actually Reitmeister and Durand, but Reitmeister originally defined this. He assigns this cohomological invariant, which is a secondary invariant to the manifold, and then it was trying to find an analytic formula for Reitmeister torsion that they discovered this quantity, and they conjectured that they should be the same based on some finite dimensional observation, which is true in infinite dimensions also. So I'm not going to tell you about this now, but let me give you an example of this at least, so that you see where, at least one example, how this can be calculated. Again, there are some nice calculations here, and then we can move on maybe. So that's the definition. Any questions?
Masoud, I have two questions, please.
Yes.
So you wrote something, I think, maybe I don't know, it's a standard, that pi1 of a space acts on the space itself. I think you used that somewhere.
What's that? Pi1 of a space acts on the space? No.
Yeah.
No. I said that fix a representation of pi1.
Okay. Then that pi1 acts on V, the finite dimensional space. How do you get action?
I see what you mean. No. Pi1 acts on mtilla, on the universal cover.
Oh, okay.
You see, the way I defined this E was that this was mtilla cross, V. So pi1 acts on this, it also acts on that. It's a kind of balanced product. So you divide And, I mean, the action of pi1 in the product is nice. And then you divide, you get a vector bundle, and that vector bundle is E.
Okay, thank you. And
yeah, what's the second question? Yeah, what was it?
I think we lost him.
Oh, is that right?
Maybe some connection issue.
Maybe, yeah, can you?
He's back.
Huh?
I can see him again.
Okay. So maybe there are no questions. Okay.
So no, actually, I have a question. So I was waiting until he comes back, but
okay, yes, sure. What is it?
Following up on the analogy between this quantity and Euler characteristic. So Euler characteristic, one of the reasons why it is a useful quantity is that it very weakly depends on the chain complex, right? So
yes.
It's a very strong invariant in the sense that very robust. So does this have similar?
No, this Reitmeister, if you want, is a secondary invariant. So let me give you something. So imagine you have a chain complex, right? You have some cohomology theory, you have a chain complex. So imagine the cohomology of this complex is zero, is trivial in all dimensions. Imagine it is trivial. So the question is, okay, what can you do with this complex topologically? It looks like it's hopeless, right? Because there is no topological information in this chain complex because its cohomology is zero. But what these Reitmeister showed or observed is that actually, if you fix some data, if you fix bases in your chains, then you can define a nice invariant, which is a secondary invariant, which has nice properties. It's not like topological invariant, but it's still is invariant in some sense. Okay, so it's a secondary invariant, and so that's why we have to assume in this case that this is I mean, assuming that this Doran thing is trivial means that actually cohomology of that M with coefficient in the vector bundle is trivial. So this is so there. Okay, so now there is about this kind of algebraic topological aspects of this. There is a very nice paper by Milnor on Reitmeister torsion. I think maybe even the title is like that. So it's very well explained. I think it's in 60s. There's a paper of John Milnor. So there's also a book on Reitmeister torsion by, I forgot his name, sorry. It's a very nice book. So that's, well, I mean, there are zillions of references, of course. So. Yeah, so, I mean, this is much deeper than Euler. And this is because it's where cohomology cannot do anything for you, but nevertheless, this will do. This will work for you after that. So it's hidden behind some walls. So yeah, that's why it was discovered much later. So, any other questions or comments?
I had a second question. Sorry, my internet again is not good.
Okay.
So you wrote omega p of m and e.
Yes.
As tensor product over C naught of m of those two spaces. So we can turn these into a Hilbert module over C naught of m, right?
Yeah, I suppose, yes.
So in the same way they introduce class in K groups, or like as unbounded cycles, or?
Yeah, I suppose unbounded KK cycles you can define by this method. Yeah, I mean these are, of course, I'm working only with the smooth ones, but so you have some dense subset of this Hilbert module, and this things works. Yeah, I mean.
Okay, and for flat spaces, I think it should be, this cycle should be product of ordinary Dirac operator on the space, right?
For flat vector bundles, you mean?
Yes, because Laplacian, because Dirac operator is a square root of Laplacian, I think we should get. Am I right? I'm just guessing something. I don't know.
Yeah, I think it's something good to discuss. Maybe we discuss it after class. How about that?
Okay, thank you.
Yeah, sure. Yeah, no. I mean, this was a good question also. So now let me give you an example that kind of gives you some sort of feeling for this at least, because it looks very. Yeah, I think examples are important to have in mind. So let's look at the case of circle. So n equal to S1. Of course, in the case of circle, you know that any complex vector bundle over S1 is trivial, right? Any C vector bundle over S1 is trivial. So now, so just flat connections if you want, but of course connections on these vector bundles, on trivial vector bundles, need not be flat. I mean, you can have a trivial vector bundle with a non-flat connection. It's not a problem. So, but flat connections. So let's assume rank is 1. I mean, so flat connections on E equal to S1 plus C, right? They are of this form, nabla equal to D, which is the usual theorem, minus IA d theta. So remember, this goes from omega 0, right, of S1 E, which is a trivial bundle, to omega 1 S1 E. And so this one, A is any real number. Okay, so what do you do? I mean, elements here are just complex valued functions, the smooth functions on S1, right? So this differentiate with respect to theta, and this one you just multiply by A and then put d theta. Why it's constant? Because I'm assuming my connection is flat. So the curvature of this connection involves the derivative of this term. It's a term. It's 0, so it has to be constant. So that's clear, right? So that's and this I is for unitarity, and this is not. Okay. So we have this. Then we can start computing this. The Laplacian of this complex now. So okay, so now let me just get my, I believe I have it here. Yes. So okay, now this one, the holonomy of this has so this is the parallel transport operation. It's essentially going to be exponential of this. So rho A tau equal to exponential of 2 pi IA. Remember, this A is fixed, belong to R. And this tau is the generator of pi 1 of S1, which is Z. Okay, so that's so this is there's a bundle here, and when you move, you don't come back to the same place because this connection has monodromy, and its monodromy is this. Unless A is an integer, this is not trivial. So it's multiplying by some phase when you move one loop around the circle. This is the monodromy, and that's. So what is so there are two Laplacians now. So this Laplacian's delta 0. So I denote dependence on A equal to delta 1 on A. So this is like, call it delta A. They're the same. So this, you just calculate the adjoint of this and multiply, then you get delta A is equal to, so delta A is equal to minus d2 d theta squared plus 2ia d theta plus a squared. This comes out to be equal to minus I d theta minus a squared. So with identical spectrum, you see in this case, 0 forms and 1 forms are identified with each other because this is a flat manifold and it's one dimension. So 0 forms are functions, 1 forms are functions times d theta, but this is a flat. I mean, this is parallelizable. So again, coefficients of 1 forms are identified with functions. So it's same. So with identical spectra, so spectra you can compute lambda n equal to n minus a squared. Sorry. Now n equal to 0, 1, 2. So now we are assuming that a is not an integer. So that's important. Because if a is an integer, then this complex won't be a cyclic. It will have some zero-dimensional kernel. That's a non-zero zero-dimensional kernel, which would be, that's not what we want. We want to assume that a is not an integer, which is, we can assume because. Okay, then what? I mean, this calculation is straightforward. Then a spectral zeta function explicitly is given by in this case, so zeta function in this case is really just this quantity zeta delta A S equal to sum 1 over n minus a to the power 2s. You see, S n belongs to Z. Huh? Yeah, here, I mean, I should have said that this guy has multiplicity 2 for n and minus n. I'm a bit worried about that, but I think this is correct. So this is equal to now sum n bigger than or equal to 0, 1 over. You want to write it over positive integers only. That's the trick we do. N plus 1 minus a to the power 2s plus sum. Okay, and bigger than or equal to 0 again, 1 over n plus a power 2s. So you can write this as, in terms of Riemann-Hurwitz zeta function, zeta 2s, yeah, 1 minus a plus zeta 2s and a. So this zeta SA is a Riemann-Hurwitz zeta function. It was introduced by Hurwitz. Is equal to sum 1 over n plus a to the power s. And from 1 to infinity, I believe. Maybe see. Yes. This is this is an important generalization of Riemann zeta function due to Hurwitz. It's called Riemann-Hurwitz. You can get it in terms of this. So now the thing is, we will, to compute this torsion, we need the derivative of this function at 0. But this is known, and it is known that use the following formula, that zeta prime of Riemann-Hurwitz at 0 is given by log of gamma of a. This is the gamma function plus minus 1/2 log of 2 pi. So it's, remember we saw, I indicated in the last lecture how to compute zeta prime 0 in terms of log of 2 pi, is 1/2 log of 2 pi minus, so without this term. Now we have this term. So you can use then this to compute this analytic torsion in this case. So for a, if I mean not belonging to Z, we get that analytic torsion is equal to T of S1 and rho A. That representation is equal to log of 1 over 1 minus rho A of tau of T squared. So which is just exponential of 2 pi I A, this one. Right. So this is one example. And this is related to the monodromy, actually, or holonomy of this connection. Because I think I wrote the holonomy somewhere. And yeah, so I think that's good for now. So I think because we didn't even have a break. So I think so this one-dimensional example is nice, but then I think it has been done in some contexts, at least in higher dimensions, some cases, yeah. So this. Okay, so the originally this was just this conjecture, but now this Shiger-Muller result plays a very important role in number theory. So that's all. So any questions or comments?